All right, grade A, welcome to your next unit, a full new unit on light and optics, really just learning all about how light works, how light behaves, things like reflection, refraction. We're going to get into the eye and how the eye works, lenses, mirrors, all sorts of good stuff. So to begin with, today's lesson is actually just kind of talking about what light is, talking about some terminology, really laying down the groundwork for this unit. So first of all, well, what is light? And you're not going to learn the full story here. You're learning like part of it, a piece of it that matches the level you're at with grade 8. And then as time goes on, when you go into high school, you're going to learn a little bit more. Okay, if you go into physics in high school, and then in university, you might learn a little bit more about light. But for now, basically what we're going to say is light is energy, which is true. Light is a form of energy, and it allows us to see the world around us, of course. And when we're talking about seeing the world around us, we're actually talking about one specific part of the electromagnetic spectrum, which light is a part of, visible light. Um, and it's basically like light waves that are between 400 and 700 nanometers, which is getting too complex. But essentially what you need to realize is that the light we see, the visible light spectrum that we're going to spend most of our time in this unit talking about, is actually just a very small piece of a larger spectrum of light. Okay, so visible light is just a small piece of the electromagnetic spectrum. And in fact, if we actually go to shorter wavelengths and higher energy, higher frequency, then we're looking at, for example, ultraviolet radiation. You know about UV rays from the sun causing skin burns and cancer and everything else. And then if we actually go to higher wavelengths and lower frequencies, okay, so more spread apart wavelengths, then we're looking at infrared radiation, which maybe you've also heard about. So we're talking about a larger electromagnetic spectrum, but what we're focusing on is just a small part of that, which is visible light. But I digress. The big thing for you to know is that light is a form of energy. Light is what we call the part of the electromagnetic spectrum that we can see with our eyes. And this is showing you the electromagnetic spectrum right here in this diagram. And visible light, as you can see, is a small portion of that, right? Small little bit of the full electromagnetic spectrum. Okay, so some properties of light that we need to know and understand. Number one, light does not have a mass. It is not matter. It does not take up space. So mass is not, or light rather, is not a form of matter. Light is a form of energy. And energy we define as the ability to do work. Now, you might already kind of know what energy is or understand a little bit of what energy is, but I think this kind of helps us to understand it, that work is done when a force, which is a push or a pull, is applied over a distance. So when I have something that has energy, it would be able to, once it gets converted or using some kind of mechanism to convert the form of energy, it would be able to apply a push or a pull over a distance. And that's what energy is. So it's able to do things. Okay, it's able to move stuff and so on if we have energy. Now with light, that would obviously take a few steps and conversions, but still, light is a form of energy. So now that we're talking about energy, let's talk about some different types of energy. Okay, so for example, we're going to do some talk about different conversions of one type of energy to another type of energy. So we need to know the names of some different types. So mechanical energy is one type of energy. And what mechanical energy is its energy of moving parts. Well, when I have things moving, that means that I have mechanical energy. So an example would be a car moving. Okay, that's an example of mechanical energy because that is something moving from one point to another point. It's moving parts, etc. Chemical energy held within chemicals. A great example of this would be a battery. Okay, so a battery has chemical energy. Now, when I actually use the battery, when I hook it up to wires or a device, then that chemical energy is turning into electrical energy, right? But it is a form of energy. So basically, it's energy held within chemicals that it then could be released through a process or through a reaction. Electrical energy is energy in electricity, which is just energy actually in electrons. Electricity is electrons that move from place to place. So when I talk about electrical energy, an example of that would be, basically energy moving through, or electrons moving through wires. Okay, so electricity, let's say in a circuit or in wires. Energy of heat, okay, is thermal energy. So something like a toaster produces thermal energy. I need a better example for this. I didn't actually give an example there. So a good example of something that produces electricity would be like a generator, right? So a generator, I actually put in mechanical energy when it gets cranked, and then that mechanical energy results in electricity or electrical energy being produced. A toaster takes electrical energy and turns it into thermal energy because it creates heat, right? So that is an example of something that would actually make thermal energy. Light, well, a light bulb would be an example of a device that makes light energy. We've already talked a little bit about what light energy is, but basically, light is a form of energy. Okay, so hopefully that makes some sense. So we're going to talk a little bit about these 5 types of energy and talk about some conversions that take place in different devices for those types of energy. So is it possible to convert one type of energy into another form of energy? Yes, very much so. And that's what happens in machines, is we're converting one type of energy into another type of energy, typically. So that's an energy conversion that's taking place. So let's take a look at some different energy conversions that would be taking place in these scenarios. So if I have a light and a black shirt, so let's say the sun, and then I have a black shirt, that the sun is shining on. So what's happening? Well, in that case, what's taking place is light energy is being converted to thermal energy. We can agree that over time, the shirt would feel hot as more and more light energy gets absorbed by the black shirt. Light in solar panel. This is another great one, right? So then I've got light energy that's hitting the solar panel, and then as it hits the solar panel, what happens is that solar panel makes electricity. So I'm going from light energy to electrical energy, right? As electrons get excited in the solar panel, and they take the energy from the light, and now those electrons are electricity being made by that solar panel. Hand generator and a light bulb, well, in that case, as I'm cranking the hand generator, I have mechanical energy of moving parts. And then the light bulb, well, actually, we're going to do this in 2 different steps. Mechanical energy of the moving parts, it's a hand generator, so that's then going to electrical energy. And then after I have electrical energy, I'm going to have light energy as the light bulb lights up from the action of the hand generator. Batteries and light bulb, really similar here. I have, of course, chemical energy to start out in the batteries. That's then turning to electrical energy, okay, as it ends up making electricity from the battery. And then finally, with the light bulb, I have, of course, light energy. So the light bulb converts electricity to light energy. And then a glow stick and light, kind of a neat one. This is chemical energy going to, of course, light energy. So some examples of energy conversions taking place. And the idea here, again, is just understanding the different types of energy, what they are, and what's happening in different devices or happening there. Okay, so let's talk about some sources of light. The most important one, of course, is the sun. The sun is a natural light source. And of course, it's what's lighting up our solar system and planet. Now, how the sun actually makes the light it does is that there are nuclear reactions happening on the sun's surface. So hydrogen atoms are actually joining together in a process called fusion in order to make helium. And that releases a massive amount of energy. So the sun is actually constantly doing a nuclear reaction. Now, all light, this doesn't just apply to the sun, all light travels at a speed of 300 million meters, sorry, not miles, but meters per second. So 300 million meters per second is the speed of light. So if 1 second went by, right, you turn on a light bulb, 1 second goes by, the light from that light bulb has gone 300 million meters. Now for the sun, when we actually have the sun letting out light, it takes about 8 minutes and I think 34 seconds for that sunlight to reach Earth. That's how far away Earth is from the sun. So because light travels at 300 million meters per second, it takes some time for the light to make it from the sun, which is super far away, to Earth. When we talk about stars, right, that we look at the night sky and we see stars, well, the light from those stars actually takes millions of years to reach us. When we're looking at stars in the sky, we're actually seeing stars as they were millions of years ago, which is absolutely insane. You're seeing things in the past. Right? If the sun were to just disappear, we wouldn't realize that for 8 minutes and 34 seconds. We wouldn't see anything different, and then all of a sudden, boom, it would be gone. But as we would see it, it would be gone 8 minutes and 34 seconds after it was actually gone. When we look at the night sky and look at all these stars, a lot of those stars are actually now no longer there. Okay, or certainly they don't look as they do now. So when we look at the night sky, we're looking into the past. Okay, and that's due to the fact that light travels at a max speed of 300 million meters per second. So let's talk about some artificial light sources. So incandescent light bulb is kind of like that old style of light bulb that is a typical light bulb that we used to use, but now actually most light bulbs seem to be LED or compact fluorescent or something similar. So an incandescent light bulb converts electricity, as all light bulbs do, to light and thermal energy. But these are really inefficient, these old style of light bulbs, and actually 95% of the energy that goes into the light bulb actually ends up turning into heat instead of light. So that's why over time these have been phased out, and they're actually now not as easy to buy as, let's say, LED or compact fluorescent light bulbs. And that's because of the fact that they are so inefficient, they waste a lot of energy. But how it works is the filament heats up, and as a result, the filament heating up, getting extremely hot right in the middle of the light bulb right here. That filament getting extremely, extremely hot, but not being able to burn up because there's no oxygen inside of that bulb, ends up getting incredibly bright, and that produces the light. Okay, that's how these incandescent light bulbs work. To compare this to other types of light bulbs, so I have incandescent here, halogen, CFL, that's compact fluorescent light bulb, and then LED, which stands for light emitting diode. And these are kind of the newer ones. So of course, LED ends up actually lasting the longest at 34 years typically. Compact fluorescent, 14 years, halogen 4.2, incandescent lasts typically just around 1.4 years with typical use. Now, this is the really shocking thing, how much more efficient these are than a normal light bulb. So this is the percent more efficient than incandescent. So incandescent is typically like 5% efficient at producing light, while halogens is 28% more than that, so like 33% efficient at producing light, which means that 67% approximately would go to producing heat. Compact fluorescent, 80% of it, right? 75 plus 5 is 80% of it, of the energy that goes in turns to light. The other 20% goes to heat. And then LED is an amazing 88% of the energy that goes in gets converted to light, and then 12% would turn into heat. So as you can see, LED, huge advantage. The big thing is that as a result of it being more efficient, it wastes way less energy. And this is probably quite telling here, lumens per watt. So this is how much energy goes in, a watt, and it produces 72 lumens as opposed to 15, and that's like a unit of light, okay, a way that we can measure light. So kind of neat to see the comparison, but this is the newest kind of most advanced technology in terms of efficiency that we have access to is LED light bulbs, and they're fantastic. Another artificial source of light would be chemiluminescence, which is when we actually have chemical energy converting straight into light energy. So light is released from a chemical reaction. The best example of this, simplest, would be just a glow stick. And this is when chemicals, stored energy within chemicals in a reaction is being released as light energy, and that's why it glows. We can see it. Okay, so really, really neat. I actually made, back when I was in university and doing labs in organic chemistry, we actually made the chemicals for light sticks and mixed them together, and we had a fun time. Then we even this probably wasn't the safest thing, but we ended up putting it all over our lab coats. So it'd be like all glowy and stuff in the dark, and it was a fun time. Anyways, chemiluminescence, really neat stuff. In biology, there are some organisms that actually have chemiluminescence inside of them. So they actually, as a result, are able to glow because they do chemiluminescence reactions. So in the deep ocean, for example, this can happen. Some organisms in the deep ocean have adapted to do chemiluminescence so that their bodies or parts of their bodies, light up. Sometimes some insects have some chemiluminescence. For example, you've heard of fireflies, right? That's chemiluminescence occurring. Really neat stuff. And it's basically what you're seeing for glow sticks, similar reactions, but happening within living things. As the chemicals mix, a chemical reaction occurs, and chemical energy is turning into light energy. So now let's get into some terminology that we need to know moving forward and talking about light type stuff. So when things emit light, they let light out, they glow, or they're a light source or whatever, we call that luminous. So for example, if I were to go back, these are luminous things, right? Because they're letting out light. Objects that do not emit light, they're not letting it out, we would just call non-luminous. They are not luminous, they're not letting out light. So of the following, is this luminous or non-luminous? Kind of funny, I don't think there's even iPods anymore. Do they make iPods anymore, or is it just all iPhones and they got rid of the iPod? I don't actually know. But okay, so iPod, what do you think? Luminous, it's got the screen, right, that produces light. A candle. Candle would be luminous. It's got the fire, right? If it's a lit candle, probably should say a lit candle, then it's going to be luminous as it's going. A firefly, I already talked about that one. That's going to be luminous. What about a mirror? A mirror would be non-luminous. Can it reflect light? Yes, but it is not emitting light. It's not the source of the light. Okay, big difference there. Okay, brightness seems like a silly term, right, for us to even talk about this because we all kind of know what brightness means. But the intensity of light, the amount of light that's kind of reaching our eyes or sensors or whatever, would be known as the brightness. If a light is far away from you, it will be, well, you tell me. If a light is further away from you, will it be more or less intense? Less intense, right? If it's further away, less light is reaching your eyes. The same light is close to you, it will be, of course, more intense. I would rather have not brightness, but this is awkward. It's better in your notes. You get the idea. It will be more intense, more bright as it is closer to you. Some other terminology that we should know, other terms. So if we talk about how light kind of travels through an object, the ability of light to travel through an object, we have three terms that we discuss. Transparent, which means light passes straight through. It's just a straight path. Can't really even see that the object is there because light just goes right through it. Translucent means light scatters as it passes through the object and some rays bounce back. So not all the rays, but some rays would be translucent. And then finally, opaque means that light cannot pass through. So light is just bouncing off of it. It's not able to get through that object as well. And things that are opaque will cast shadows. Things that are translucent will pass shadows somewhat, right? But opaque means a full-on shadow. So this is a great diagram kind of showing this. Very cutesy, but transparent, you can see his face. Translucent, you can see her face a bit. Opaque, no face. There is no face seen. Okay, so face, little face, no face. Let's talk about shadows. First thing to understand is that light travels in straight lines, and we call these rays, right? So you've probably heard of like sun rays and light rays. So that's what we call the light traveling in a straight line as a ray. Rays cannot travel through opaque materials. That's the definition of opaque, is that light cannot travel through it. So because the light cannot travel through and it's going in a straight line, that's why we have shadows, is because essentially the object that's casting the shadow, the light can't travel through it. So there's a dark spot where the light couldn't go through. you can use the ray model to predict how big shadows will actually be. Okay, so we can take a look and actually figure out using a little bit of trigonometry and math and stuff. We're not going to do that, don't worry. But we can figure out how large a shadow would be expected to be. That's something that we can do. So here's a diagram. We have light source, and then of course you can see all these rays, right, going through. But if we have an object that's opaque and the rays can't get through for that object, ta-da, then the wall will, as a result, have a shadow on it wherever the rays could not get through that material. And that's how shadows work. So I would have a shadow essentially from, of course, here, right, to here. Big old shadow. And that's because the rays cannot get through our opaque object. So here's a question for you. How do you increase the size of a shadow? Let's say you're trying to scare a sibling by making some spooky animals with your hands. Okay, if you want to make it larger to make it seem more intimidating, and you've got a flashlight, you want to put your hands closer to the flashlight or further away from the flashlight to make it as big as possible? And the answer is you want it to be as close to the flashlight as you possibly can. The closer it is to the light source, the larger the shadow is going to be. If you want to decrease the size of a shadow, well, then you have the object, the opaque object, further away from the light source, and then as a result, okay, the shadow is going to be smaller. So that's a little bit of how shadows would work. This is a great diagram kind of showing this. If I have the object closer to the light source, well, then I have a larger shadow, right? Which I'm seeing right here. This diagram doesn't show the fact that, light is actually coming from the flashlight to here and here. So I would have light areas here and here. But yeah, I would have a shadow that's quite large because the object is very close to the flashlight. If I have the object further away from the flashlight, well, then in that case, I would have a smaller shadow, which all makes sense. So that's a lesson for today. It's a bit of a hodgepodge, right? It's all over the place. But basically, summary here of what you should have gotten out of this is, number one, you should understand that light is a form of energy. You should understand that the visible light that you see is a small part of a larger electromagnetic spectrum, okay, that includes things like ultraviolet, infrared, gamma rays, etc. There's all sorts of different electromagnetic waves, but we are able to see visible light, which is a small portion of that spectrum. You should understand that there's different kinds of energy, like mechanical energy and thermal energy and electrical energy and chemical energy, and that we can convert to or from light energy from those other types using devices. So for example, if I want to turn light energy into electrical energy, well, that's going to be a solar panel, right? A solar cell. If I want to turn chemical energy into light energy, well, then that's going to be something like a glow stick. Okay, so I can convert different forms of energy from one form to another form. And it would be good if you were able to kind of understand what those different conversions are in different devices. Another thing you should understand is all the terminology that we went through. So understanding things like luminous and non-luminous, you should understand the opaque, transparent, translucent stuff, and then also about brightness, right? More bright, less bright. Just the term of brightness means that more light is there. And then finally, you should understand how shadows work. That when we have an opaque object, right, then that as a result causes a shadow to be made because the light cannot travel through that opaque object. So the absence of light that cannot travel through the object is what gives us our shadow. Well, that's it for today. Hopefully you understood. Have a good one.